right, everyone, welcome back. So for our first invited talk, we have Bastiaan Cnossen from the University of Wageningen, and he's going to be telling us about an axiomatization of infinity categories. All right.
Yes, I'd like to thank the organizers for inviting me to this conference. I'm very excited to talk about this project. And I want to start by saying that I'm actually not a type theorist, unlike many of you. I come from homotopy theory. I'm working on infinity categories, but it's exciting to maybe build a bridge between the homotopy theory side and the homotopy type theory side. And I like to talk a bit about what we have been doing. So an overview of the talk is going to be, I should also emphasize everything that I'm going to say is joint work with Denis Szalczyński, Kim Nguyen, and Tashi Walde. Nowadays in practice, it's mostly with Denis Szal and Tashi because Kim unfortunately has left math, but in the initial stages of this project, it was very much involved. So our project is trying to obtain foundations for higher category theory. Eventually, we're hoping that there is some type theoretic implementation of this. But for now, what I want to talk to you about today is more some kind of meta theory, which is much easier to use for beginners and also for maybe non-experts that are trying to learn the field. And in particular, maybe uncommon to usual type theoretic approaches, we don't sort of start with a fixed framework in which we make all the details very precise. We try to sort of be agnostic about what the precise underlying theory is and keep it flexible, and then maybe later we can go on and sort of develop this. Or maybe others can do that. And I should say I'm going to talk about some axioms that we are introducing, but some of them are still evolving. It's an ongoing project. Okay, so maybe before diving into any of the theory, I should maybe clarify, maybe some of the audience is not familiar with the concept of infinity categories. And maybe you have heard the notion of 2 category, 3 category, and then you think it's a generalization of this, and that's not really the right way of thinking about it. I prefer to think about it as some kind of homotopical version of category theory. So we are trying to just do category theory like we're used to. I'm hoping that most of you will be familiar with the concept of ordinary category theory at least. But now all the strict equalities that appear, we want to replace them by equalities up to homotopy, like the same concept as in homotopy type theory where you have equality types, and the notion of equality is really data that you have to provide. We want to take this and do category theory with this in mind. And maybe a different way of thinking about it has already been mentioned in the first talk. It's like some kind of directed version of type theory. So it's a version of HOT where each of the types doesn't only have like equality types, but it has hom types, which are sort of directed equality types. So, and we should have some kind of composition of morphisms that is unital and associative. And why are these objects relevant? Well, they arose in algebraic topology to describe certain structures that we were observing for describing like topological spaces up to homotopy equivalence. And they become more and more prominent in also neighboring fields, algebraic geometry, representation theory, etc. They are important, becoming more and more important. So now the next question is, why do we want to axiomatize it? And let me start by giving sort of my motivations as a homotopy theorist, which is that currently there is some kind of mismatch between the foundations on which this whole theory is built and the way that we use it in practice. Currently, the models that we use are mostly quasi-categories, and Jacob Lurie has written a whole book about how to do infinity category theory, basically using set theory, which is, I mean, it's amazing that this exists, because otherwise we wouldn't have this theory, but somehow it doesn't quite fit the spirit of infinity category theory, because set theory is very strict. You can talk about strict equalities and all these lifting conditions that you have in quasi-categories are sort of very strict, and somehow this makes it very technical to learn, and it doesn't really fit with the way that people like me are actually using infinity categories in practice. in practice, infinity categories really just behave like ordinary categories, and you just have to be careful what you mean by equality. If you just always replace equality by some kind of data, then you're basically fine. So we would like to, eventually we would like to have different foundations, but as a first step, we would like to just have a language that expresses this sort of the way that experts already are using infinity categories. And that's what I'm gonna describe to you in today's talk. Maybe some design criteria should somehow be easy to learn for beginners, should also be easy to use for non-experts that don't want to read all of higher topos theory to be able to work with infinity categories. And another thing that we are aiming for is that the resulting theory doesn't just capture infinity category theory like the usual infinity category theory, let's say, but also variants called parametrized infinity category theory. Somehow these are things that come up where you have a whole family of infinity categories parametrized by some infinity topos, and they often behave, the resulting theory of those often behaves very similar to ordinary infinity category theory. Okay, so this is maybe some motivations why homotopy theorists care about it, but I also want to sort of give a reason why maybe as a type theorist you might care about this, which is, it's the problem of theories that can eat itself. In homotopy type theory, I think this has been an open problem for a while. I'm not an expert on this myself, but if I understand correctly, it's not so clear how in homotopy type theory you would define, for example, the notion of a semi-simplicial type or other infinite structures. And I think it's very plausible that if you have an axiomatization of infinity categories instead of infinity groupoids, then these problems won't really arise. So in this case, the universe is going to be itself an infinity category. It's going to be the infinity category of infinity categories. And all the axioms that you should state, they should all sort of be satisfied in the universe. I'm not sure if this applies to other formalizations, but at least the axioms we choose are all satisfied in the infinity category of infinity categories. And a big difference with homotopy type theory is that we can talk about, the universe can talk about morphisms of types. So instead of just having the infinity groupoid of infinity groupoids, which it only talks about invertible morphisms of types, this infinity category of infinity categories has this more additional flexibility. In particular, for example, if you now want to define simplicial types, you first have to define delta as a subtype of the universe, and then you just define it as a function from delta up into cut. Of course, it needs some theory of up and so on, but this will be part of what we're going to do. Okay, so let me now go back to this thing that I mentioned about this meta language and how it contrasts with maybe other approaches of formalization that sort of build specific, what I would like to call maybe a choice of substrate. So I want to think of sort of the formalization process of as consisting of two steps. First, I want to understand what is higher category theory? What are the core principles of it? Currently, there's this whole theory of quasi-categories, but a lot of it is just specifics about the model. It's not really what the theory is really about. So this is the thing that I'm going to talk about in this talk, but I do want to say a bit also about interpretations of these axioms that we're going to say. For example, so if you choose set theory, then you can work in the model of quasi-categories. This is sort of the classical approach. Another way of doing this is you start by assuming that you know what category theory means, and then you can, for example, define a notion of infinity cosmoid. This was defined by Emily Will and Dominic Verity, and then build inside some infinity cosmoid, build all your theory infinity categories. A different formalism is the one by Joyal, the formalism of tribes. It's also a category satisfying certain axioms. It tries to capture the semantics, it's sort of a categorical semantics of type theory. And then thirdly, there are type theoretic approaches, and I'm sure that there are people in the audience that have thought about this, and I'm sorry that I didn't list you because I don't know about all the approaches, but one that I want to mention in particular is simplicial type theory by Wilf Schulman. It is basically designed to be type theory that can deal with categories. I mean, maybe more generally, like some kind of simplicial types. Some of them will be categories. And there are variants of this triangulated type theory by Gratzer, Buchholz, Weinberger. I think we might see a bit of this in the next talk. But then maybe there are different ways of taking our axioms and putting them into some version of type theory. We are hoping to get some version of type theory where all the types are categories. This also has some additional problems, and it's not super clear how we deal with it. So this is really some kind of thing that should be left to the future for now. And then there are some other approaches I want to mention. Egbert Rijke and Ivan Kobi are trying to work with globular types and see if the axioms can be formulated in there. There is some Munich people working on just trying to write the axioms directly in Agda. And I'm sure that there are other ideas out there. Okay, so yeah, let's zoom in a bit. So okay, before I'm actually going to talk about the specifics, let's clarify a bit how it relates to, for example, the approach using tribes or the approach using simplicial type theory. So this sort of meta setup that I want to describe, the categories are just primitive notions. We don't assume some kind of type theory and take them to be types. We also don't assume that there is some category such that the infinity categories are objects of that category. So I'm not sure if everybody is familiar with this concept of a tribe. I don't want to really define it, but the most important thing is that there is some category E. You have some notion of fibrations, satisfy certain properties. And in principle, you could start with such a tribe and try to formulate all your category theory internal to that tribe. That's one approach. Another approach is to take a suitable version of type theory, for example, simplicial type theory, take your categories to be certain types. And in both of these cases, if you state universal properties, you're going to probably formulate them either as universal properties with respect to your category E, or maybe you're going to state them using inference rules and so on. And in both of these cases, you can usually deduce all the coherences. But somehow we want to be a bit agnostic about this, and we're just going to impose only the low-level coherences by hand, the ones that you sort of need in practice, which, ultimately, it's not maybe how you will want to formalize it. Sort of goes against the spirit of homotopy type theory a little bit, where you want sort of the system to allow you to deduce everything that you need, but at least it's sort of it should be interpretable in sort of very many different foundations. And that's sort of for now just the goal. Okay. And then one final thing before I talk about the actual axioms is sort of, I want to give a bit of an overview of what we can actually do with it. It's just not just abstract theory. We have actually written down already a lot of actual category theory inside the system. For example, there's theory of junctions, limits and colimits and Kahn extensions, localizations, the notion of cofinality, and equivalence theorem A and B. If you're not familiar with all these words, it's not going to be relevant for the rest of the talk, so don't worry. Yoneda embedding, piano arithmetics, the notion of co-Cartesian fibration and Cartesian fibrations, and straightening and unstraightening. This will be some kind of consequence of some kind of directed univalence. And maybe in quotation marks, in principle, all of homotopy type theory should be also contained in it by taking the infinity groupoids. We didn't write all of that up, but so that's why it's in quotation marks. And yeah, then in the future, we hope to extend this, talk about prosanoval categories and topoi, and start doing some actual homotopy theory inside this, stable homotopy theory and higher algebra operator theory. And basically, after setting up all these, all the foundations that are mentioned above, the later parts aren't going to be that difficult anymore, because the way they are written in the literature, very often people have already written them in a way that don't really refer to any specific model. So it's just a matter of, maybe the couple of missing ingredients, we need to make them precise. There's some thing about filtered categories and so on, but yeah. I actually gave a lecture course last semester about stable homotopy theory, and I tried to formulate it as much as possible already with these axioms. In a couple of instances, I still needed to refer to Laurie's book, for example, for things that we didn't prove yet, but hopefully, eventually that will be fine. Okay. So now let's talk about the actual axioms that we have. First, what do we take as primitive notions? We have some notions that we just take as primitives in the theory, which are synthetic categories, functors between them, notions of natural isomorphism between them, and then for every level you're never allowed to say equal. So whenever you want to say, for example, the two natural isomorphisms are equal, you have to say that they are naturally isomorphic. Some two isomorphism or something, and then the three isomorphism and so on. And this is really just, in homotopy type theory language, this is really just homotopies and homotopies between homotopies and so on and so forth. And we also impose that there is composition and identity that satisfy associative and unitality. So, of course, if you work in some kind of homotopy type theory system, then this will all sort of be, you will have composition because you can define it using the way that these contexts work and so on, and then you can just prove that it's associative. But we just take this notion as a primitive in the theory. Next step is that we need some basic constructors. So we can always form the initial category and the terminal category, products and co-products, pullbacks, and functor categories. And again, we are sort of just gonna introduce them with their naive universal properties. So, and it turns out that this is basically enough to develop the whole theory, which a priori might seem a bit surprising. But for example, for the terminal object, what we're gonna say is every infinity category C has a functor into the terminal category. And for any two such functors, F and G from C to the point, they are naturally isomorphic. And a priori, you might expect to have higher coherences as well, that every two natural isomorphisms should be the same, etc. This we don't impose. Somehow it turns out that the theory sort of thinks that it's still satisfied. Like, it turns out that you don't really need this in practice. And similarly for products, if you have two morphisms, F from E to C and G from E to D, we impose that there exists some morphism F, G to the product. And we also impose that whenever you have two maps into the product and they're both of their components agree, then the maps themselves already agree. there are some computation rules that you also need to impose, but I didn't write up the whole actual rule. And similarly for functor categories, functor into the functor category can be defined by joining over and writing down a functor from E times C into D. So, and sort of roughly, like, to give you some idea of why this has a chance of working, is that with just these rules, we can already prove things like the functor category into the product is equivalent to the product of functor categories. So why should we be able to prove this? Well, an equivalence only needs the data of a map in one direction, a map in the other direction, and a proof that the composites are isomorphic, naturally isomorphic to the identity. So to write a map from left to right, we are mapping into a product. We can use the universal property of the product, and we just take the map induced by the projections from C times D to C, and the map from C times D to D. Then to write a map in the other direction, we are mapping into a functor category. So by universal property, we can just adjoin the E over, and then you can also write down, using the evaluation, you can write down a map in the other direction, and then to check that the composites are the identity is also, it uses the uniqueness statement for all these axioms, but we don't need any of these higher coherence somehow. Okay. So next up, so this is all the same as in homotopy type theory. There's no directedness yet. How do we talk about morphisms in categories? So for this, we're just gonna introduce a new type. It's called, so sometimes in the literature it's called delta one, because sort of historically because of simplicial sets. I want to think of it as the poset, which has two objects, 0 and 1, and 0 is smaller or equal than 1, so there's an error from 0 to 1. And let's call this the walking morphism. Now we just define a morphism in a type C to be a functor map from this walking morphism into C. And then we write that it goes from X to Y if evaluated at 0, it's isomorphic to X, and evaluated at 1, it's isomorphic to Y. So here maybe I should clarify, because the notion of object wasn't taken as a primitive, I define an object to be a functor from the terminal category into C. And then this object bracket 1, it comes with two functors from the point, one that selects 0 and one that selects 1. And by f of 0, I really mean sort of the composite. I mean, every functor will have an effect on objects. You can just compose your morphism X with f, and that gives a new object in the target. So, and also this notion of isomorphism, it's really an isomorphism of natural transformations from the point into C. I hope it makes some sense. By the way, feel free, because I'm not used to giving talks in type theory conferences, and some of the notation maybe is completely different from what you're used to. Please feel free to ask. I don't want sort of all of the audience to sort of not understand. Okay. So this talks about morphisms. Now we need to know about commutative triangles, and we're going to do the same thing. We're just going to introduce the universal commutative triangle called the walking commutative triangle, which is just a poset bracket 2, which has three objects, 0, 1, and 2, and 0 is smaller or equal than 1, 1 is smaller or equal than 2. And the commutative triangle in C is just defined as a functor from this poset from this category into C. And then of course triangles should relate to morphisms. We should have that we have three edges, and those are encoded by the degeneracy map. The three phase maps, the I. And we also have two ways of projecting the poset delta 2 to just bracket 1, which are called the degeneracy maps. So at this point, let me maybe relate this with the approach of simplicial type theory, because this is sort of here we just impose a finite list of conditions and we sort of just impose it by hand. An alternative approach is simplicial type theory, in which this falls out of a more general formalism where you have cubes and you can define subtopes of these iterated cubes and so on. And there you can just define all the simplices. They are definable and you can prove all the simplicial identities. So in particular, this will be interpretable in simplicial type theory, but this is sort of a little bit more ad hoc by hand, but it should be sort of interpretable in whatever, like basically whatever theory of categories you can imagine, you should at least have this data around. Okay. So it's all well and good to have this notion of commutative triangle, but it should still somehow behave like, why am I justified in calling it a morphism? In what way does it behave like a morphism in a category? And to guarantee this, we are going to impose three I like to call them diagram axioms. But the first one is called the commutative square axiom. Technically, it says that if you look at functors from the cube, by the cube I mean delta 1 times delta 1, into C, then we can restrict it to the upper triangle, and we can restrict it to the lower triangle in the cube. And those restrictions, they always agree on their diagonal. So we get a functor from this functor category on the left to the functor category on the right. And we are asking that this is an equivalence. So roughly speaking, this means that if you give me two commutative triangles in C, the upper half and the lower half that agree along that diagonal, they uniquely glue into a square. So, and this is useful, for example, for defining the max and the min functions on bracket 1, which allows you to, for example, eventually prove that 1 is a terminal object and 0 is an initial object. But it has, I mean, it's just really useful to know that functions out of a square are just two triangles glued together. So, yeah. So informally, let's summarize this by saying categories understand how triangles relate to squares. That's the first axiom. The second axiom deals with composition in categories. So it's called the Siegel axiom. And it says that the restriction functor from the category of commutative triangles in C to this pullback on the right. This pullback on the right is just a category of pairs of morphisms in C whose source of the first one agrees that, I mean, the target of the first one agrees with the source of the second one. And you can always restrict a commutative triangle to just the two morphisms F and G to go from left to right. And I mean, the second axiom imposes that this is an equivalence. So in other words, every two composable morphisms can uniquely be glued, I mean, extended to a commutative triangle. And this is how you define composition in your C. So given it F and G, you extend it to such a commutative triangle, and then the bottom edge of this triangle, we're going to call it the composite of G and F. And it's sort of unique. I mean, by the fact that this is equivalence, it's unique up to homotopy. I mean, even sort of up to contractible groupoid of choices. Yeah, so let's summarize this by saying categories believe that any two composable arrows have a unique composite. And maybe, you know, let's write out a bit more how this composition functor, like you can actually turn this into a composition functor. So let's introduce the Hom groupoid of a category C by defining it as the following pullback. We have the category of morphisms over there. That's just the functor category from bracket 1 into C. Then we can, I mean, the evaluation map at 0 and 1, it's sort of really composition, a precomposition by a certain functor. So that's given to us by the other axioms about functor categories and products and so on. Then we can form this pullback. And then because this morphism on the left was assumed to be an equivalence by the Siegel axiom, we can sort of turn it around there. It has an inverse, and we can look at what this composite morphism does on fibers. And then you will precisely get composition functor from the Hom in C from Y to Z times the Homs in C from X to Y to the Homs in C from X to Z. Yeah, so here we have another difference with the approach of simplicial type theory. In simplicial type theory, you don't want to assume that all your types are Siegel types. That gives problems with like dependent products and so on. If I'm understanding correctly, so this is not assumed as an axiom for all types, but somehow we just want to have a theory that describes categories. So we do impose that all types are like satisfy the Siegel axiom. Okay. Yeah, and you can prove that this composition is automatically unital and associative, so it really behaves like composition in a category. Okay, and then thirdly, we have the RESP axiom. Sometimes it's known as univalence for categories. And what this is saying is that for any type C, a certain functor from C into its category of isomorphisms is an equivalence. And this functor sends X to the identity on X. So what is this category of isomorphisms? You can again write it as an iterated pullback, but if I just wrote that expression, I thought maybe it's not super intuitive, and I prefer to just give you the pictorial picture of it. So the data of an object in this isomorphism category should be a morphism F, together with a left and a right inverse. The right inverse is G, the left inverse is H, together with data that witnesses that G is the right inverse, and you're given an isomorphism between FG and the identity, and isomorphism between H, F, and identity. And this I wrote it in words, but you can write it in a way that only uses pullbacks and all the other constructors. So this is actually a well-defined category, and then you can obtain this well-defined map from left to right. So yeah, so this is sort of saying we can think of isomorphic objects as sort of equal, which is of course something you're very much used to in homotopy type theory. Okay, so let's sort of see where we are so far. We have some primitive notions, some basic constructors. We impose some directedness, and we have some diagram axioms. And so far, this is fairly similar to all the structure that is already in Real Schulman's article about simplicial type theory. It's just that we don't impose a lot of this additional type theory background. It's sort of more down to earth in a way. And with just this structure, you can already develop some basic theory. You can develop the notion of adjunctions, initial, terminal, objects, slice categories. In principle, you can also define limits and co-limits. And more fancy notions like Cartesian and co-Cartesian fibrations. And this has already been written up. So I realized that maybe the word formalized, maybe you use the word formalized differently. I think there is actually a formalization approach in RLZK. I don't know how far they are with proving all this material. In any case, this is written up in articles by Real and Schulman and Buchholz-Weinberger. Okay, and now we want to go on and we have to impose, to do actual category theory, we need more constructors. And a very important one is going to be the groupoid core. Whenever we have a category C, we should be able to throw away all the non-invertible morphisms to obtain a groupoid. So maybe let me define what a groupoid is. So groupoid, what it should mean is that all your morphisms in your category are invertible. And because we have this Rask axiom that says that the isomorphism category is equivalent to C, we can nicely formulate this by saying that the functor from C to its arrow category is an equivalence. This is the functor that sends an object to the identity morphism. And the universal property says that for any other groupoid that maps into C, there is a factorization through the groupoid core, and two such factorizations have to be isomorphic. Maybe here is a good point to mention that there is some, if you want to eventually turn this into a type theory, then this is one of the axioms where there are some subtleties, because you cannot assume the groupoid core to exist in arbitrary contexts. So you have to deal with this somehow. There is a notion of crisp type theory by Mike Schulman that deals with this. That was written up in the case of continuous structures on types. The same formalism should probably work to deal with this groupoid operator. And then there was also some version of model type theory that probably Daniel will talk about in the next talk. So I'm sweeping sort of this notion of context a bit under the rug, but this is a point where it's actually going to matter. Okay, and then with this groupoid, let's also give a name to the groupoid core of the functor category. Let's just call that the mapping groupoid between two types C and D. Okay, so that's the first constructor. The second one is that we should be able to form subcategories. If we have some collection of morphisms, by a collection of morphisms, I really mean that we have a monomorphism from some groupoid M into the groupoid of arrows in C. So notice that I'm using map instead of fun. And we need to condition that this collection of morphisms is closed under composition. So that means that the composition operator on map 1, C, if you apply it to things that are in M, then the result is again in M. And similarly, if you have a morphism in M, then the identity map on its source and the identity map on its target are also in M. Then if you have this, there is some new category bracket M subscript C that maps to C, which has the universal property that all its morphisms are sent to morphisms contained in M, and it's universal with this property. So any other category that maps into C, if on morphisms it lands in this class M, then it has to factor through this category. A priori, the axiom doesn't assume it's a subcategory, but a posteriori, it is a subcategory. Like it is a monomorphism of categories. Okay. A third thing we need is localizations. If we have some collection of morphisms, we should be able to invert them to obtain a new infinity category. And this is again just specified by a universal property. And maybe it's good to sort of make a difference between these last two axioms, universal properties of those, and all the earlier ones. Because before I was sort of emphasizing that we only impose these naive universal properties. But from this moment onwards, we can sort of use the theory we already have to phrase all the next universal properties. For example, now that we have the mapping groupoid between infinity categories C and D, to define a universal property of subcategories, we can really phrase this as a pullback condition on mapping groupoids. I mean, maybe I should have actually written it on the slide. Yeah, you can this uniqueness condition of factoring through the subcategory. You can really write it as a certain pullback of categories. So from this moment onwards, we're sort of moving away a bit from the super naive universal properties, and they become a bit more coherent already. Okay. And then for completeness, let me also state that if you invert all morphisms in C, what you expect is that you get a groupoid. And it turns out this is not completely formal, because in this process of inverting the morphisms in C, you might have created some new morphisms a priori. So this is also imposed as an axiom. The result that you get after inverting all morphisms is a groupoid. And this is sometimes called the geometric realization of the category. Sometimes it's also called the fundamental groupoid of the category. And then the final constructor we need is the notion of joins. Roughly speaking, you take C times the interval times D, and at time 0, you squash all of D to the point, and at time 1, you squash all of C to the point. And finally, I feel like I'm going very quick. I hope I haven't lost everybody. There's always a danger with slide talks that you just rush through them and then nobody has time to read what is on them. So I apologize for that. Anyway, so finally we need 3 more axioms that relate to fibrations and that talk about universes. The first one, we call it the functionality of universals axiom. And the precise way of formulating it is maybe not the most relevant thing. The most relevant thing is sort of the concept behind it. Sometimes you want to construct functors, and in ordinary category theory, you can sort of actually just do it by hand. You tell where all the objects go, and you just say where all the morphisms go, and you check some properties. This is not feasible in infinity categories anymore. Definitely not if you're working in some kind of synthetic system. But sometimes you get this for free. If your object satisfies some universal property, they will automatically assemble into some functor. And that principle is what this axiom is trying to capture. And we are not sure if this is the most optimal way of phrasing it. Somehow it seems a bit technical using this formulation. But let me just spell out what this version says. It says that if you have a co-Cartesian fibration from E to C, and you assume that all of its fibers have a terminal object, then actually all these terminal objects assemble into a functor from the base category C into E, which is a section. So composite of P and S is the identity, and it's actually right adjoint to P. So maybe if you want to think of this co-Cartesian fibration, some kind of type family over C, for every little c, we have some type E subscript C. then we are assuming, I mean, and the co-Cartesian somehow says that it's covariantly functorial in the base. And the condition says that each of these types have some terminal objects. And then the conclusion that we can draw is that they are somehow functorial in C. They give an actual family of terms of each of this type family. It's like a section of the type family. Okay. Yeah, so let's summarize this by saying that families of initial and terminal objects automatically assemble into functors. And this is a very important principle because it allows to reduce a bunch of properties. Like we can check a bunch of properties on objects. For example, a priori notion of a terminal object in a category, you might say something like the slice over the object is equivalent to C itself, or other ways of formulating it. But using this principle, you can reduce it to the statement that we are used to, namely for every other object X, the Hom groupoid from X into the point is contractible. This makes it match with the way that we use category theory in practice. Okay. Then we have the exponentiability axiom, which says that every Cartesian or co-Cartesian fibration is exponentiable. Maybe in terms of type theoretic language, this says that we have dependent products along this map P. And this in turn, you can think of it as whatever formulation you prefer. Another way of saying it is that the pullback along P, the slice category of infinity categories over C to infinity categories over E has a right adjoint, satisfying some Back-Chevalier conditions. And this is maybe important to emphasize. The theory of categories behaves quite differently from the theory of infinity groupoids because we don't have all the dependent products. For example, for an arbitrary functor, it's not true that this pullback functor preserves all colimits. So it cannot necessarily always, it cannot possibly have a right adjoint in that case. And I think this is probably one of the subtleties that need to be dealt with if you are trying to formalize this. A way that simplicial type theory, for example, deals with this is just by introducing more types. You allow types that are not categories, and then you do have dependent products and certain problems go away. Secretly, we are hoping that it is still possible to have some type theory, like because we still have certain dependent products. We hope that there is some type theory that allows us to just work with only the categories. But at this stage, it's unclear, and I would be very happy to talk with any of you that has ideas about this. Okay. And then finally, we have the directed univalence axiom. So what it says is that we have sufficiently many, so this is maybe in quotation marks, what sufficiently many means, but directed univalent universes, U bullet to U. So there, I should explain two things, what I mean by universe and what I mean by directed univalence. So by universe, I mean that it is closed under all the previous categorical operator, like constructors that we have introduced. So it's closed under products, co-products, contains the initial terminal categories, closed under functor categories, closed under groupoid cores, etc. And by directed univalent, this is a variation of the usual univalence axiom. It says that the Hom groupoid in U between types C and D, so really, I'm abusing notation a little bit here. So really the C and D on the left should now really be terms of the universe U. And then given terms of the universe U, you have to define what the big C and D are, but you can define them, I mean, the pullback of this map P. Yeah, so there's some details that I'm sweeping under the rug here. But there is a canonical map that you can write down from the left to the right. where the right is this mapping groupoid that I introduced earlier. So this is sort of just in the meta theory. This doesn't live internal to the universe. And we are asking that this is an equivalence. And why is this a version of univalence? Well, if we now restrict to equivalences on both sides, the invertible morphisms in U, they are equality type of U. And on the right, this is the type of equivalences between the type C and D. So then in this case, this is really the version of univalence axiom that you're used to. Okay, then I'm basically done. So let's just give an overview again of what we have discussed. So I've introduced some kind of meta language for talking about higher category theory, based on primitives, constructors, some basic axioms. All of them are very much mirroring the way that they are used in practice, which makes it hopefully much easier to learn this for students and for non-experts. And an upshot is that all these axioms should be interpretable in various foundational systems. And we are hoping to get some input from the type theory community, what would be suitable foundational systems in which to develop all this theory. And in particular, as I've emphasized already before, we would very much hope that there is a type theory which just is the type theory of category theory. But of course, we would also be happy with developments of simplicial type theory and other things. And the final thing, let me mention that everything that we have written down so far can be found in the book project, which you may find on my website. Okay, let's end here. Thanks for your attention.
All right, we have time for a few questions.
Yep. So I guess with infinity category, you meant always infinity one category.
Yes.
And on the previous slide, you had this directed univalence.
Yeah.
And do you have any hope of having a version of your theory where it is even more directed in that instead of map, you can get functors? Or is this, then you kind of have infinity two categories, but is this maybe possible at least as a hack? I guess this is something people would want in the application side.
So I think I think that would be very interesting to have an approach that directly deals with, for example, infinity two categories. Probably if you want to include infinity two categories, you directly want to go all the way, include infinity three, infinity four, infinity. And I personally haven't really thought about this so much. I think the notions of infinity categories that are used in practice a lot by researchers are mostly the infinity one categories, basically because of the reasons I mentioned before. It's the same way that categories are much more common than two categories, where you have non-invertible maps. In practice, the same way infinity one categories are much more common. And somehow, you might ask, okay, isn't it more natural to regard the universe cut as an infinity two category? And the answer is, well, yes, that is more natural, but we don't really need it for the formalization because already the universe cut as an infinity one category can already talk about natural transformations because we have morphisms in the functor category. So for the development of the theory, we didn't really need it. And yeah, I don't have to say much about general theory of infinity n categories, unfortunately.
Okay.
Okay, so on that same slide, I don't get if the certain functor that you talk about is canonical or if it's part of the data for the directed univalent.
That's not part of the data. So what you can do is, so this is sort of a pointwise formulation of the axiom, But what you can also do is you can write a functor from the arrow category of U. The arrow category is the functor category from the Walking morphism in Q. And you have to map into some kind of type of co-Cartesian fibrations over U times U. And this is not part of the data. You can define this using the properties of co-Cartesian fibrations. Somehow, it's some kind of straightening procedure. It's a bit technical. I don't think I will manage to describe it right now, but yeah, it's written up in the book project. But the most important thing is that it's definable, not part of the data. Yeah.
Thank you. That looks very interesting. Actually, first of all, thank you for clarification to the answer to Felix, because I was a bit confused because when you said infinity categories, but you do work with infinity one categories, yeah? Is this right?
Yes. So in the literature, it's like among homotopy theorists, the common convention is that if you say infinity category, you mean infinity one category.
So I have just one other question. Is everything you do constructive? Because I mean, you had this axiom, what was axiom 7? It looked a bit like you had a choice, or maybe it's a misconception.
Should I go further back or further forward? Wait, I guess go forward, right? Yeah. This one. So this can be made constructive. You could write introduction rules, or I mean, I would have to think about how you would directly translate this to type theory. But
it doesn't start.
I mean,
the type theory axiom flows is also okay.
no, so it really depends a bit on how you define on objects and so on. And the way we deal with this is basically, okay, I defined in the beginning that an object is a functor from the terminal category into C, but somehow that's not really what's going on. To get a well-behaved theory, we define objects to be more generally functors from an arbitrary groupoid into C. And then whenever you say the statement holds for all objects, what you're really saying is you pull back the statement, like you regard it as in the context of that groupoid, and then you make the statement there. So in this case, what it's going to say is that if you pull back this fibration to the groupoid core of C, then you have a section, and then you impose that you get a section also on of P. But maybe your question is like, there seems to be a choice involved in saying that. I mean, yeah, but hopefully it clarifies. So when I say we have the terminal objects for all little C, it's sort of already like the way that we phrase this already encodes the functionality of all these things somehow. But I mean, for an average user, they don't necessarily need to. I mean, somehow the reason that we choose to formulate it in terms of objects is just because it matches the way that people are used to working with object level statements. So. Sorry if that was confusing.
I think we're out of time for questions. So let's thank the speaker.